Yes, dear friend, this is a monkey bar session for lateral directional case. You could see this is Cessna 206. What type of wing it has? It has, we call it high wing, right? And if you see the Hansa 3 airplane, and this sort of an airplane is having a wing which is called low wing. You see the contrast, low wing, and there's a high wing, okay? And if I see another airplane, which is back of Cessna 206, that is also a low wing, but having appreciable dihedral, that is wing, low wing, or some dihedral is given. Okay. These are important aspects for giving lateral stability to the airplane, right? Also, you should understand that vertical tail, which is here, whole is a vertical tail. This is extremely important for giving lateral stability. And for lateral control, you have aileron, which is here. This is the aileron. You are familiar with it. This is the aileron up, aileron down. And also we have a rudder. If you see this rudder, if I turn it like this will give a force in this direction that will take the airplane towards left, yaw the airplane towards left. If I do it like this, the airplane will be yawed like this. Okay? So these are the control surfaces for lateral control. Primarily is the aileron, which is here, and rudder, which is there. If I come back to the Cessna 206, you will see here the aileron is somewhere here. It will be always near the wingtip. This portion is the aileron, up and down, up and down. And this is the rudder. Here it is rudder. See, it goes towards left, goes towards right. And you could see it's very appreciable size of vertical tail. You could see this is rudder, and please carefully see the rudder is this portion. Right? A total, when I take total area, is the vertical stabilizer. And rudder is almost 40% of the total area, 35 to 40%. So rudder has to be very powerful, because if it doesn't have that enough power, then if the airplane has gone into a stall and if it is spinning, then the aileron will not be effective. So that time the rudder will be used to counter the rolling. You could hear background sound of airplane taking off. So we always love it. We want this sound to be there all the time. So before I go to the class, let us revise again. As far as aileron is concerned, it is supposed to give rolling moment. And when right wing is going down and left wing is going up, that configuration we say rolling moment is positive. For yawing moment, right wing going back is yawing moment positive. With this understanding, we now go to the blackboard and try to understand few things which we have perhaps missed or not clear. That is why this is a monkey bath session. Yeah, we have come very long distance, and today we are having a monkey bath session on directional lateral static stability. Okay? You know that we have seen what do you mean by static stability. You know, if there is a initial tendency to come back to the equilibrium once it's disturbed, then you say it possesses static stability. So for directional case, what was the understanding? For directional case, we said if I am flying the machine like this, this is the relative wind B, and this is beta. We are revising the directional case, and in directional case, what do you say? If I watch my hand, if I am flying like this, right, then I say beta is 0. Beta means side slip angle, that is, if the airplane is actually, CG is actually having motion like this and also going forward, right? That is side slip. That is, if you see here, this airplane, if I put my if I'm moving like this, then beta is 0. But if I'm moving like this, okay, then that is the configuration. Here, beta is positive. What is beta positive? Very common mistake we make. Beta positive, the best way to understand is, when I'm moving, if the relative wind is coming from my right side, right, then it is beta positive. Remember this, okay? This is beta positive. Now, the point is, suppose the body was, or the airplane was moving like this, because of some disturbance, there is a beta introduced. What should be natural tendency if it is statically stable? So it should immediately generate a moment like this, right? That is right wing going back. That means it should generate a positive yawing moment, correct? Positive yawing moment. And you know by now, you know the coefficient is Cn, right? In a totality, what we say, this means Cn beta should be greater than 0. This will ensure directional static stability. This is clear, right? Please understand that this is very important derivative. It has to be very well controlled, because if it is too high, then the airplane will become too sensitive to crosswind. You don't want that, no? Because our wind is coming like this, then the beta is positive, it will turn like this. Wind is coming from this side, it will turn like this. That will become miserable. So you have to have very clear understanding what is the magnitude of C and beta I am going to design the airplane for. Then we discuss about C and delta R. Right? What was the C and delta R? Very easy to understand. Remember, for longitudinal case, we had Cm alpha, which is static stability. Then we have Cm delta E. This was elevator control power. So what was the understanding? Understanding was, this man is static stability parameter, and this is a control parameter. Understanding was, if this man is very high, then if keeping everything same, I have to put larger control power to change from one trim to another trim. Because if Cm alpha is highly negative, statically stable, it will not allow it to go from one trim to another trim, or it will resist change from one trim to another trim. So that was the relationship. So, similarly, C and delta R, we have seen this is the rudder control Similarly, C and delta R is the rudder control power. Okay, and its sign, what is its sign? Check your lecture notes. It's very simple. We have already discussed. First, we decide what is the sign of delta R. Delta R is positive if I'm flying like this and rudder is deflected towards left. If it is deflected towards left and is moving like this, force will act in this direction over the rudder, and about CG, it will give a moment like this. If you look from the top, isn't it? So that means the airplane will turn like this. And you know yawing moment positive is this, right wing going back, but in this case, this is left wing going back. So this yawing moment is negative. So for a positive delta R, yawing moment is less than 0, and hence C and delta R sign is less than 0. Correct? Please keep at back of your mind, for longitudinal case, Cm alpha less than 0, Cm delta E less than 0. For directional case, C and beta is greater than 0, and C and delta R is again less than 0. Right? Now I ask you a question. Suppose you want to fly, we want to fly or trim the airplane at a given beta. It's possible I'm going like this, so there is crosswind is coming like this. Say this is small v and this is u, and the beta introduced will be how much? Will be v by u, roughly, right? So I want to fly at a given beta. So what will be my configuration such that my whole directional control is activated? That is, I will fly such a way that Cn will be 0. Trim at beta equal to, it's a v by u, right? Means at this beta, Cn should be equal to 0. Like when I say trim at alpha, what do you say? Cm must be 0. Trim. No Cm should be available there. So now we know Cn I can write as Cn beta into beta and Cn delta R into delta R. Please understand, what is Cn beta into beta? It is coming from the fact that this airplane is statically stable. So if I'm flying like this, if there is a wind coming like this, which gives me beta, and because of static stability nature, it will turn, it will tend to turn. I don't want it to turn. I have to hold it. So what I will do, I will give it a moment Cn delta R into delta R such that this is nullified. That means the moment given by this delta R and moment because of stability, that sum should be equal to 0. So I can find out delta R is equal to minus Cn beta into beta by Cn delta R. Okay? Now, interesting thing, please understand. If I want to trim the airplane at a positive beta, what is the sign of Cn beta? It is positive. Sign of Cn delta, negative. So what is the sign of whole of this term? For a beta positive, positive, negative, 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 positive. So delta R is positive. Meaning thereby, if I want to fly, if I am flying like this, I want to fly like this, then I have to put the rudder towards left. That's all. And then I will get a configuration where I am flying like this. Is this part clear? Okay. Now, this was simply, I was talking about your rudder control, and rudder, if you remember, one of the important things which rudder should do is engine failure case. Okay, let's also revisit that. It's very important. This is the wing, and let's say this is fuselage and all. Now the important aspect in the directional case is basically for twin engine airplane. Right? You know, in twin engine airplane, there are two engines. Let's say both are having same thrust, but there is a possibility that one of the engine can fail. Right? I must have enough rudder power. I must have enough single engine power so that I can maintain an altitude. I don't turn like this. Right? So for that, what is the way to handle it? What we will do is, if this distance is A, this distance is A, then suppose this has failed. So then, what is the moment given by one of the engine about CG? Is T1 into A in this direction. Correct? Then how and in what direction I have to generate a moment to counter it? It will be in this direction. Right? So I have to put the rudder in this direction. If I put rudder in this direction, it's a delta R. Then the force will be in this direction. That will give a moment in this direction about CG. As long as the moment given by the rudder and balances the imbalance moment because of one engine fail, my aircraft will still remain like this. I have to increase the throttle definitely to see that lift equal to weight. Okay. But as far as yawing moment is concerned, I see that T1 into A plus Cn delta R into delta R, they should be equal to 0. But please note down, this statement philosophically is correct, but dimensionally they are wrong. This is Cn delta R non-dimensional. This is dimensional. So what I have to do? I have to divide it by half rho v square x into b. So now this becomes non-dimensional. Cn delta and delta is 0. So I know what is the delta R required. That is minus T1 into A by half rho v square SB 1 by Cn delta R. So this tells me that when I design an aircraft, I know the thrust, this much of delta R should be available. This delta R should be less than the delta R max, because delta R also has a limit. I cannot go on deflecting the rudder like this. At some point it will become brake. The intermediate point, the flow may separate. So there are some delta R max, which is less than equal to maybe 25 degrees, plus minus. Okay, or modern aircraft, they have increased to 40 degrees also. But point is, you should be very careful as a designer that I need to have sufficient delta R or the radar deflection which can account for thrust asymmetry. This is also one of the important role of the radar, and you can understand easily what is the importance of Cn delta R. If my Cn delta R is high, then delta requirement will be less. Okay? So that's why you find that many airplanes have got huge radar, right? Once directional is over, let us revisit lateral stability. Please understand, when we are talking about longitudinal stability, then there is a horizontal tail which gives a restoring moment. When we are talking about directional, we have seen the vertical tail primarily. But for lateral, there are no such surface. So we have been telling this, what happens if the airplane is going like this and there is a disturbance in the roll, that is about x-axis. As it rolls like this, the lift vector gets tilted, so it starts side slipping. As it side slips, since the vertical tail is here, that will generate a moment negative like this. This is clear? This we have explained with a lot of, if you see this with a lot of effort, because see, suppose this is beta. Where from this beta has come? This beta has actually got induced because there is a roll disturbance like this and it starts side slipping. The moment the beta comes here, this will give a force coming out of this plane, and that will try to give a rolling moment negative. That exactly I want. I'm moving like this because disturbance, I want it should generate a moment, it should do like this. Initial tendency should be like this. So disturbance, side slip, vertical tail, it comes like this. So we say for lateral stability, CL beta should be less than 0. It's very, very important. And how do we achieve this? We have seen we achieve this through vertical tail, number 1, number 2, wing. And what is that wing? We talk about high wing, talk mid wing, talk low wing with dihedral. You can have some sweep effect also, and typically you have seen for vertical tailless airplane which are designed to have minimum RCS to avoid radar inceptions. Sweep is given. You see sweep will generate some CL beta negative. It generates some CL beta negative because no vertical tail. Sweep gives CL beta less than 0, and especially very important contribution when there are no vertical tail. Now let us see how high wing was giving CL beta negative. You have seen this is the high wing, and if I demonstrate you will understand. Suppose this is the fuselage and this is the high wing. It has banged like this, starts side slipping, the air will gust in here, it will push the wing, it will generate a negative rolling moment. So for a positive beta, negative rolling moment, so CL beta is negative. Right? If CL beta is negative, then the aircraft is statically laterally stable. Please understand, we give a phi disturbance to check lateral stability, and because of phi, there is a beta introduced, and high wing will give a CL beta negative like vertical tail. Okay? We have also seen that something called dihedral, that is, if this is low wing, they are not giving much of lateral stability. But if you give a dihedral here, right, then you can get CL beta less than 0. This is also extremely important. Thank you very much.